Earth is a nuclear planet. Chapter 5. Waste not, want not. Nuclear power's primary mission is to ensure a reliable and sustainable supply of clean energy for the nation and the world by replacing fossil fuel with the smallest and cleanest possible footprint. A key part of this process is to wean the world off of coal by producing energy cleaner and cheaper than coal. Nuclear is already doing this. It just needs to be doing a lot more of it, and in a lot more places. For nuclear power to be a genuine long-term solution, its sustainability model must include the reduction, or much better, the elimination of uranium dirt mining, coupled with the freedom to recycle so-called spent fuel rather than sending all of it to long-term storage. We'll discuss this more in Chapter 18. The good news is that uranium mining can be significantly reduced or even eliminated through any combination of these 5 technologies. Number 1, exploit our depleted uranium as fuel for fast neutron reactors. Number 2, recycle spent nuclear fuel in fast neutron reactors. Number 3, breed new fuel from feedstocks of natural uranium and thorium. Number 4, reprocess used fuel for another round in light water reactors. And number 5, extract uranium from seawater to fuel existing and future reactors. Reprocessing used fuel for a second run in light water reactors like France has been doing for the last 40 years is the low-hanging fruit that could cut uranium mining waste nearly in half. After its second run, the twice-used fuel can then be processed and used again in fast neutron reactors for a complete burnup. The alternatives listed above could all be in widespread use by mid-century. Before we dig any deeper into the subject of energy derived from fuel, we should take a moment to refresh those cherished high school memories of ions and isotopes and the difference between chemistry and nuclear physics. But this time, let's do it with lots of pictures and almost no math. Be sure to refer to the images on the website as we go. First off, you can think of isotopes like cars, identical models of the same sedan, but with different engines. Hydrogen is a simple example. Most hydrogen atoms have nothing but a single proton in the nucleus and a single electron orbiting that nucleus. And that's it. When people refer to hydrogen, this is the isotope they're thinking of, protium, or hydrogen-1. Think of it as the protium, hydrogen's base model ride. Some hydrogen atoms have a neutron in the nucleus to keep the proton company. That's the deuterium model. Tritium, or hydrogen-3, is a rare limited-edition hydrogen isotope sporting twin neutrons under the hood. But so long as it just has one proton, it's only a hydrogen sedan. Your neutrons may vary. Chemistry is all about the electrons and does not involve the nucleus of any atom. All chemistry does is rearrange the electrons orbiting the atoms involved in the chemical process. Electrons are negatively charged, and the protons in the nucleus they orbit are positively charged. An ion is a custom version of an atom's basic model. The ionization process offers a variety of trim packages that give the atom a greater or lesser number of electrons whizzing around its nucleus in a cloudy blur. Changing the atom's electron count will give it a formal minus charge or a formal plus charge, depending on whether electrons were gained or lost in the process. Hydrogen, for example, typically has one electron orbiting a solitary proton. This protium atom becomes a free-flying proton when its electron is stripped away. That's how the sun, our first operating fusion reactor, showers us with cosmic rays. Metals such as lithium tend to lose electrons and become what are called cations, and some elements like fluorine tend to gain electrons and become what are called anions. A chemical reaction can alter an atom's net electric charge by removing or adding electrons, turning the atom into a positive or negative ion of its former self. This can make it attract or repel another atom, depending on the other atom's charge. Chemical energy comes from breaking and forming electron bonds between the atoms involved in a chemical reaction. The process either gives off energy, called exothermic, or it absorbs energy, called endothermic. But either way, the field of chemistry is all about the electrons. Nuclear energy, as the name implies, is all about the nucleus, and is typically produced by splitting a uranium or plutonium nucleus with a free-flying neutron zooming along at just the right speed. Because it has no charge, a neutron can zoom undeterred through a thick cloud of electrons and strike a target nucleus. The neutron could be absorbed, but if it splits the nucleus instead, some of the binding energy that held the nucleus together is suddenly released. Some fast-flying neutrons will zoom away from this high-energy event as two new, smaller atoms are formed, sometimes three, with most of the original electrons settling into orbits around the new atoms. Zooming neutrons, whether fast, slow, or in between, are the projectiles that crack open the nuclei of heavy atoms, which, conveniently enough, eject one or more zooming neutrons as they split into smaller atoms, and thus we have controlled chain reactions. But not to worry, it is impossible for a reactor to have a runaway chain reaction like a bomb. Fuel enrichment levels are far below the required concentration, at 4 to 19% versus 85% or higher for nuclear weapons. The energy we get from combustion, such as burning wood, coal, diesel, etc., comes from the sudden rearrangement of electrons when carbon atoms and oxygen atoms react. The energy derived from fission comes from the splitting of some of the largest atoms in the universe. Think of it like this. The electrons of a large fissionable atom are like a swarm of TIE fighters protecting the Death Star. Chemistry is when the TIE fighters engage in a dogfight with the X-Wing fighters of the Rebel Alliance fleet hovering nearby. Nuclear is when Luke obliterates the Death Star with a proton torpedo down the thermal exhaust vent. Except nuclear fission uses neutron torpedoes, and the nucleus doesn't get blown to smithereens. It just breaks into a pair of smaller atoms, sometimes three, and one or two neutrons, sometimes three, go zooming away as well, along with the release of a stupendous amount of energy. But you get the idea. Section 5.1. Meanwhile, back on planet Earth, to make fuel pellets for a light water reactor, uranium is chemically extracted from uranium-bearing ore. The resulting yellow cake powder is purified natural uranium, a metallic powder that's 99.3% uranium-238 oxide and 0.7% uranium-235 oxide. While uranium-238 will not fission, uranium-235 will, and this is best accomplished with a slow-moving or moderated neutron. Any neutron is fast and furious when it zooms away from a fission event, but maintaining its speed, and thus its energy, depends on what it bumps into. Conveniently, water molecules do an excellent job of slowing down zooming neutrons to the proper speed for splitting uranium-235. The idea of fissioning U-235 in a water-moderated reactor to make steam to spin a turbine to make electricity was a logical first step in early reactor design. The result was the light water reactor, or LWR, a workhorse technology virtually impervious to climate or weather and capable of generating on-demand energy for about 2 years straight before refueling. Plutonium-239 can form when uranium-238 absorbs a neutron. This is because while U-238 is not fissile, it is fertile, and can thus be bred into plutonium-239, which is an excellent reactor fuel. Cultural note: a bunch of 20th century guys came up with these terms. Though it rarely happens, a bit of Pu-239 can also be formed when the U-235 in fuel pellets absorbs multiple neutrons instead of fissioning. But however it's made, the heavier plutonium-239 isotope typically requires a fast or unmoderated neutron to fission. for a number of technical reasons we'll explore in our upcoming book, Power to the Planet. The plutonium-239 that forms in a fuel pellet only has a 40% chance of fission in a light water reactor. But even so, plutonium is such a terrific fuel, it burns hot, as they say, that more than 1/3 of the energy produced in a light water reactor comes from breeding and burning plutonium. Note, burning is the 1950s slang for fissioning nuclear fuel. This is known as the uranium-plutonium fuel cycle. The remaining 60% of the plutonium-239 that forms in a reactor's fuel pellets will just sit there, gobbling up more neutrons like immobilized Pac-Man, turning into larger and larger isotopes, plutonium-240, 241, 242, and so on. Higher elements will also be produced, such as americium-241, the radioactive material used in smoke detectors. Aside from plutonium-239, however, most self-respecting transuranic isotopes wouldn't even consider fissioning with anything less than a seriously fast neutron. And that's where complications arise. Section 5.2. Transuranics have nothing to do with exploring Uranus. Transuranics, or TRUs, are the man-made elements that lie beyond uranium on the periodic table: neptunium, plutonium, americium, curium, berkelium, etc. They're down in the bottom row, separated from the main table. Nerd note: the periodic table primarily organizes elements by their proton count. All isotopes of uranium, for example, have 92 protons. That's what makes them uranium atoms. But the table also organizes elements according to how many electrons occupy their various orbitals, arranged as shells within shells like a Russian doll. Nature has some very clever ways of fitting electrons into these orbitals, but in simple terms, lanthanum and actinium begin their respective rows below the main table because they are the first elements with F electron orbitals. Since there can be up to 14 electrons in the F orbital, placing these oddball elements in the table would make it too unwieldy, so they're depicted in separate rows below the table. Only a handful of the actinide isotopes are long-lived. These troublesome TRUs come about when the plutonium-239 that forms in reactor fuel absorbs even more neutrons without splitting. It's these long-lived, man-made isotopes that make used fuel seem like such a vexing problem, even though it's actually not. For one thing, the longer the half-life, the lower the radioactivity, and thus the lesser probability of harm. Along with the smattering of these long-lived isotopes, used fuel also has a collection of short-lived fission products, or FPs, newly minted atoms that are too small to fission. They form when big fuel atoms split in two, and some of the resulting FPs are harshly radioactive. Since fission product atoms are formed from much larger atoms, and since these humongous atoms are held together with an overabundance of neutrons, an FP will usually start life with several more neutrons than its elemental peers. Radioactive cesium-137, for example, versus plain old cesium-133. Fission products shake off or radiate this extra baggage so they can settle into their new life as smaller, normal atoms. When fuel atoms split, the fission products that result tend to occupy two distinct regions of the periodic table. Figure 33 on the website shows this quite clearly. Sorry, alchemists, but gold isn't on the list. That's not how the nuclear cookie crumbles. The problem with FPs and TRUs forming in fuel pellets is that they're pretty much evenly distributed throughout several tons of very mildly radioactive U-238 filler, which constitutes about 95% of the typical fuel pellet. This is why all used fuel is treated as long-term radioactive waste, although, considering the amount of energy produced per kilo of fuel, the volume of used fuel is downright minuscule, even from reactors that only burn 3% of their total fuel load. See figures 31 and 34 on the website for graphics on this. The good news is that both used fuel and depleted uranium can be recycled and thoroughly fissioned in fast neutron reactors. This is different than reprocessing used fuel for another round in slow-spectrum light-water reactors, which for all their stellar performance are inefficient fuel burners. The unmoderated neutrons in a fast reactor can break down, or compost, the 100,000-year transuranic waste that forms in used fuel into 300-year fission product waste, producing gigawatts of power in the process. By using fast neutron reactors, the U.S. would have enough so-called spent nuclear fuel for about 180 years of electricity at the nation's current rate of consumption. However, we should note that processing and recycling used fuel for complete burnup in fast reactors would be considerably more complicated and expensive than using depleted uranium. Section 5.3. Depleted but far from spent. Depleted uranium, or DU, is the leftover material that results from the solid fuel enrichment process for light water reactors. Several batches of natural uranium yellowcake must be depleted of their uranium-235 to enrich a single batch, which is then made into fuel pellets. The depleted uranium from which the U-235 has been separated is currently regarded as waste, but our nation's stockpile of DU is actually a treasure trove of fuel for fast reactors. However, there's just one hitch. You need 8 times as much fissile material to kickstart a new fast neutron reactor than you need for a new slow neutron reactor. This is because the faster a neutron flies, the smaller every fissionable target nucleus seems to be. This means a fast reactor needs a lot more neutrons to get the party started. Nerd note. From the viewpoint of a zooming neutron, the perceived size or cross-section of a target nucleus is largely determined by the speed of said neutron, and is measured in barns. The term comes from the wry observation that if a neutron is going slow enough, every target nucleus will seem to be as big as a barn. To a fast neutron, however, a target nucleus may seem to be only 1 barn wide rather than its actual width of 8 barns. This, of course, makes the target 8 times smaller and thus 8 times harder to hit. The solution is to throw 8 times more neutrons at the target. Thus, the initial fuel load for a fast reactor is about 8 times the startup load of a slow-spectrum reactor like the light water reactor. Another way of looking at it, you'll need 8 bags of briquettes to fire up the grill. But once a fast reactor is up and running, it can gradually start breeding more and more of its own fuel from an increasing diet of depleted uranium or used light water reactor fuel pellets, which are about 95% depleted uranium-238. See Figure 35 on the website for a good infographic on fuel processing. With proper care and feeding, a fledgling fast reactor will mature into a self-sustaining compost bin for nuclear waste. Having to build a bonfire in order to have a weenie roast is why fast reactors should always have a slightly positive breeding ratio. That is, instead of being a so-called isobreeder that makes just enough fuel for its own use and not a smidgen more, a fast breeder reactor would breed a little more fuel than it actually needs and set it aside. Depending on the breeding ratio, there will eventually be enough set-aside fissile to kickstart another fast reactor, without mining, refining, and processing a humongous new 8-time startup load. And not to worry, the stockpiled fissile material from a breeder will be a mix of quote-unquote reactor-grade plutonium and other actinides. Great for nuclear power, but useless for nuclear weapons. With fast breeders making extra startup fuel to power their own build-out, our depleted uranium waste could serve as a long-term supply of free fuel for a national fleet of fast reactors. We have hundreds of thousands of tons of the stuff, about 5 or 6 times more than all the light water reactor fuel we have enriched since the 1950s. Unlike slow neutron reactors, which tend to be picky eaters, fast reactors will eat everything they're fed, and the mining has already been done. Nerd note: natural uranium contains only 0.7% of the scarce U-235 isotope fissioned in existing slow neutron light water reactors. To make a batch of low-enriched uranium, or LEU, to fuel a nuclear power plant, several batches of yellowcake powder are converted to uranium hexafluoride gas, UF6, and spun in a cascade or sequence of high-speed centrifuges. Spinning at 50,000 revolutions per minute, a centrifuge separates the uranium hexafluoride gas ever so slightly, with the heavier U-238 gas tending to drift toward the outside. The lighter 235 gas tends to remain a bit closer to the center, and being a bit lighter, it will also tend to rise toward the top. This top gas is drawn off and fed to the next centrifuge, and so on down the cascade, thousands of times over, with a tiny bit of separation and thus enrichment in each step. When the desired enrichment level is finally reached, the U-235 top gas and the U-238 bottom gas are chemically converted back into separate batches of solid uranium oxide. The enriched yellowcake powder made from the top gas is then sintered into fuel pellets. This means applying dry heat and pressure to form a dense, insoluble ceramic. The depleted uranium powder made from the bottom gas is set aside as waste. Since depleted uranium is nearly pure uranium-238, it's only slightly radioactive and can be easily transported on public highways. However, regulations have made it nearly impossible to transport more radioactive used fuel to either a recycling facility or to a deep geologic repository, or DGR. This overabundance of caution is in spite of the long demonstrated safety of transport casks, which can withstand the direct impact of a rocket-assisted locomotive. It should be noted that when used fuel is transported to a reprocessing facility, recycling this spent nuclear fuel into another round of reactor fuel requires sophisticated shielding and handling, both of which are expensive. So while either depleted uranium or spent nuclear fuel can be used to generate power in a fast reactor, depleted uranium is a lot less hassle all around. And like any country that enriches uranium, the U.S. has a lot more DU than used fuel. Indeed, after processing low-enriched reactor fuel for more than 60 years, the U.S. has accumulated about 750,000 tons of depleted uranium. If this was fissioned in a fleet of fast reactors, it could power the nation for more than 1,500 years at our current rate of electricity consumption, or about 600 years when we transition to an all-electric society. See our supplement on depleted uranium reserves. But don't take our word for it. Here's how climate scientist James Hansen puts it. Quote, "With the fourth generation of nuclear power, you can have a technology that burns more than 99% of the energy in the fuel. It would mean that you don't need to mine uranium for the next 1,000 years." End quote. In the long run, we think that depleted uranium will prove to be more popular than spent nuclear fuel for fueling fast reactors. As we see it, the widespread recycling of used LWR fuel will probably only be done if the public insists. And to be fair, the public just might insist, because thoroughly recycled used fuel would produce gigawatts of clean power while also reducing its radioactive longevity from 100,000 years or more to 300 years or less. See Figure 36 on the website for a graph on this. In any case, the radioactivity in used fuel is not the looming rectify or die threat to humanity that it's often made out to be. It is true that the half-life of plutonium-239 is 24,000 years, and as we saw in Chapter 3, it takes 10 half-lives to render a radioactive material harmless. So this does mean that the plutonium-239 in used fuel will be radioactive for 240,000 years. Now, at first glance, this might seem like a showstopper for nuclear power all by itself. But the actual hazard window for human health and safety is significantly shorter than that, despite any fear-mongering to the contrary. In fact, after just 600 years, all penetrating gamma radiation is gone. From that point forward, you would literally have to grind the stuff up and inhale it or ingest it for the remaining alpha and beta radiation to do you any harm. After 1,000 years, the radioactivity of used fuel would be no more intense than the mine from whence it came. So if scavengers in some far-flung future ever do go through the trouble of exhuming used fuel from an ancient repository, they would also need nuclear chemists and engineers to process and refine the stuff into any sort of significant threat. And if they had the technology to do that, they would also have the technology to make plutonium in a production reactor from a bit of yellow cake, and they would save themselves all the excavation and chemistry. Like most scare stories about nuclear power, the unsolvable problem of nuclear waste isn't a problem at all, unless it's been made into one.